Okay, we begin Unit 3 of our calculus course with the section entitled Linear Approximation 4-6. So, what is this going to be? Just like it's been this entire chapter, it's yet another application of derivatives. So we're not going to really jump right into formulas just the second. What I want to do is I just want to talk about a little bit of logic with you. So let's just say that we have a typical curve like this, and then we have a tangent running through that curve. So in pink, you see that. Where is that tangent intersecting the curve? At the point P. So clearly they share a value of y at this point. It's the only value of y that they share, actually. So that's where we start. Now, let's just say that this was on some type of graphing medium, calculator, whatever it is, and we decided to zoom in on that area over and over again. So let's say we zoom in once, and then all of a sudden you can see the curve is just flattening out a little bit because of the zoom job, and we get something that looks like this. And then we zoom in again, and then you can see the curve is really flattening out. Why is it flattening out? Because we're basically only looking at the curve zoomed in right here, right? So what is the key concept here? Well, it says, in summary, if you zoom out on the graph of the function at the point P, the curve seems to approach the tangent line at that point. Using this understanding, we should be able to use the line tangent to the curve at some point P to approximate the value of the function of the points, keyword, near P. Okay, so what does that mean exactly? So if I have, let's say, a point on the curve, just like that, and I don't know in this scenario what that point is, I could use the point on the curve, the point on the tangent, in order to approximate the value of those points, because the curve and the tangent are so close to each other near the points P. So near this point right here, they're so, look at it, it's so close to another. Is it exact? No. But it's so close that we could use a linear approximation in order to figure out what the points are on the curve. That is what linear approximation is about. Okay, so what could we do? So pictures here again. Basically, let's say y is equal to L of x, which is our equation of our tangent, essentially, our value, and then we have our function. So what is this? How do we find the linear approximation? It's actually by this very simple formula. Now, you might not see it as simple in the beginning, but it really is. So our linear approximation, L of x, which is going to be essentially how we approximate our curve, is going to be equal to f of a plus f prime of a times x minus a. Now, this is actually point slope formula, but in a different sort of, what's the word? It's like a mirage. So what if, in this equation, I just subtracted f of a over? What would I get? I would get this. We're not going to do that when we do problems, but this is what I would get. So what are we looking at? So this is y right here. So remember, y equals L of x. F of a is going to be our value of y. F prime of a is the slope. And then x minus our value of a is always our x1. So if you look at this, look at the similarities. This is actually just the point slope formula, but in a different visual. It's just formed in a different way with a couple variables different. So this is what we use in order to approximate values on a curve, let's say if we can't find those values. Okay, it says before we actually work through some problems, it's essential that you completely understand linear approximation and what it's trying to do. So let's say right now we have a curve right here, which is f of x is equal to x squared plus 1. And let's say we have a tangent line, which is g of x equals 4x minus 3. Okay, so it says both of these are drawn through the point, the tangent point, 2, 5. So basically, at x equals 2, we know that the value of f and g are both equal to 5. We know that. If you want to sub it in, 2 squared plus 1 is 5, 4 times 2, 8, minus 3 is 5. We know that has to be the case because they both share this point, 2, 5. But what about the values near 2, 5? So like values in here, let's say. So how do we feel about those values? So what I did was I took this yellow region and I basically zoomed in on it. I'm actually a little bit off here. Just give me 1 second. So I took this region right here, this region, and I zoomed in on that region super, like a ton, and I got this graph right here. So all I'm looking at is basically like what's going on right here on the graph. So it says below, so look at this, here's the 0.25, right? So that's here. And then the rest of these are points at 2, 1. So it says the graph below shows the same exact graph, but zoomed in on the 0.25 and immediately to the right, as I stated over here. It says specifically the graph focuses on the values 2.1, 2.2, and 2.3. So 2.1 right here, 2.2, 2.2, 2.3, 2.3. What we're looking at is the function values for each one of those points. And what we want to do is we want to sort of analyze the y value. So look at this. So what's the y value for the curve? So the blue line is the tangent. The curve is the, I guess it's a red or orange line at the top. So on the curve, which is x squared plus 1, so I'm going to write x squared plus 1 here, and 4x minus 3 here. So on the curve, we get 5.41 if we put 2.1 in. But the tangent reveals 5.4. That's only an error of 0.01. So it turns out that there's only an error right here in our approximation of 0.01. So what about the next two? Well, now we're on the curve, we have 5.84, but the tangent estimates it to be 5.8. So right now we have an error of 0.04. Now clearly, does everybody see, like, just like this line and this curve are falling away from each other, the same thing is happening here, but it just seems less because I'm zooming in. So that is an error of 0.04. If we go to the next one, 2.3, the error is 0.09. So clearly the error is going to increase in our estimation as we move away from the value of 2.5. I mean, duh, right? That's a no doubt. So the key is would you feel comfortable in this standpoint estimating this curve with this tangent in the points near? Well, I would say that these aren't so bad. I don't mind. That's not too bad an error. Don't love it, but not bad. So I would say, yeah, we could use a linear approximation to estimate the curve's values, but just got to be really close to 2 to do it. So just to go crazy in the other direction, right? So what if we went to 3? So let's say let's get rid of this. So let's say we went to 3 and we picked the points right here. So if we plug 3 into here, we're going to get 10 as our result, right? 10. And if we plug 3 into here, we get 9 as a result. So 10 and 9. So would we feel happy about estimating, using the line to estimate this curve at 3? I would say not at all. So if you're literally a single unit difference, that is a big error. So we want like microscopic errors. These aren't even microscopic, but they're small enough. But 1 unit means we would never want to use this line to estimate this curve at 3. We need to be super near 2 in order to make this work. So that is the logic about approximation. That is what we do. So the question is, how about examples, right? Let's do some. So a very popular example in a lot of textbooks is the idea of using finding approximation of a radical when you don't have a calculator. Okay, let's think about that for a second. So what if no calculator available and you need to find an incredibly accurate approximation of root 97? Okay, so what would most students do? I think most very sharp students would be like, oh, well, the square root of 100 is 10, so the square root of 97's got to be 9 point something really high, 9.8, let's say, something like that. Well, that is an excellent guess, but it's not incredibly accurate. So that is where linear approximation comes into play. So let's start with root 97 comes from the function root x, right? So it's a square root function that we're using. So what I have here is the graph of the square root of x, just so that we have a nice look at what we have to do in the scope of our problem. All right, so remember, we have a formula for estimating what this value is going to be. So if we go back to our formula, let me find it, it is right here, right? So I'm going to show you what that is about so that you understand how to use it in a linear approximation. So we have L of x is equal to f of a plus f prime of a times x minus a. Okay, this is our approximation. So what would we do? So it says our goal is to approximate the value f of 97 equals root 97 without using a calculator. Therefore, we need to value near x equals 97 that we already know the square root of. That clearly will be the value x equals 100, which we usually refer to as a. Okay, a. Now note, look at the formula. It has a lot of a's in it, doesn't it? So that's important. Therefore, what would we do for our values? So we would say find the linear approximation of f of x equals root x at the point a equals 100. So how would we accomplish that? We would want to find the equation first. So what would we do? Well, think about our equations. We need f of x. F of x is root x. So what we need to find f of 100 plus f prime of 100 times x minus 100. Okay, that is our goal. That's what we need to do. So what is f of 100? Well, that is plugging 100 into root x. So this is root 100. What's f prime of 100? Well, we don't know that. Why? Because we have to find f prime of x first. Well, what's the derivative of root x? Well, I told you to memorize that. That's 1 over 2 root x. If you need to do that out every time, then remember you're changing it to x to the 1/2 and you're doing the power rule. But if I want to put f prime of 100, I need to put 100 in there. So I'm going to get 1 over 2 root 100. And then multiply by x minus 100. All right? So all we have to do is simplify. So we're going to get 10 plus 1 over, it looks like 2 times 10 is 20. And we're going to get x minus 100. And if we distribute, we're going to get 10 plus 1/20th x minus 1/20th of 100 is, I believe, it's going to be 5 for the scope of our problem. So finally, we're going to end up with 1/20th x plus 5 when we combine this and this as our value. So our L of x is equal to, our linear approximation is the line 1/20th x plus 5. Alright, so we just produced the linear approximation, but what does that actually mean? What does that mean on the picture? Okay, that is the key. You got to know what it means. If you know what it means, it's going to make life easier for you, so that's where we're going to go next. So, if we look at our picture, this is the square root of x, right? So right now, what is this problem asking? This problem is asking for us to go to find what the value of y is when x is 97. So when x is 97. So you'll see I labeled 90 and 95 right here. So 97 is going to be about right here. Okay? So what is this problem asking for? This problem is asking for the value of y at 97. We don't have a calculator for that. We can't do a square root with easy math. So we kind of don't have an avenue to do that. So instead, what do? We find a value that we do know by heart what the square root is. So we go over to 100, right? And what we do is we develop a line, a tangent line that goes through 100 of our graph. Like this. Okay, it goes right through our graph. Guess what? That's this. Okay, that equation is 1/20th x plus 5. Okay, now, what we need to do now is, even though they share, these two lines are going to share a point at 100 in our standpoint, note that they're going to not share any other point. So even though this line right here looks like it's right on top of the other line, it really isn't. Really, it's going to be something like this. It's going to be something more like this, where we're going to have to use, we need to plug in 97 into our tangent line in order to make a guess about what it is on the actual curve. Now, this would be a poor example because it's far away, but look how close the tangent line and the curve are to one another over here. That's good. So that's what we have to do next, is we have to estimate what the approximate value of f of 97 is by subbing into our linear approximation. So we need to find L of 97, which is going to be 1/20th times 97 plus 5. Yes, I mean, hypothetically, you could use a calculator, but you don't need a calculator. We could sit here and just do, long division, and we could figure out 20 into 97. So what you're going to get, basically, when you add this together, is you're going to get 9.85. Okay, so this is our linear approximation for the square root of 97 using the tangent line, the green tangent line, instead of the curve. So since we couldn't find the number directly on the curve, we used the tangent line, which is flying right by it and very close to it, in order to approximate it instead. Okay, but, so the whole key is here is, how accurate is this, right? So it would be pretty neat to know what kind of error that we created here. How far off was this? How close was it? Because it seems like we're doing something that's kind of bizarre to find a value like that. So how close were we to estimating the square root of 97? Well, we can use a very common percent error calculation to handle that, which is normally 100 times approximation minus exact over exact. So just to be clear, what numbers are those? Well, our approximation is going to be our linear approximation, right? And the exact value is kind of a misnomer, just because technically that's going to be the approximate value. I know that sounds weird, but basically that's going to be your original value that we know of. Like if we put root 97 in the calculator, what do we actually get? Well, let's see. So 100 times. So our linear approximation was 9.85. But if we substitute root 97 in the calculator, we can do that as is, right? So and it's over root 97 as well. By the way, this is approximately 9.8489. So hopefully this kind of blows you away a little bit. So look real quick. So this is the value we got with the approximation, and this is the actual root 97. Look how close that was. That is, when I first learned this, I thought that was pretty cool. To be able to find a radical without actually finding a radical, pretty neat. So if we actually do this calculation, we're going to get approximately 0.01%. Yes, not 1%, but 0.01%. Hugely accurate. So very little error involved with this calculation, which is a great thing. We were able to find a pretty accurate estimate of root 97 by using another radical that we actually know the square root of, 100. Now, obviously, we have to be careful here. So if we were using root 100 and we wanted to estimate, let's say, root 92, that would not probably be smart. The farther we get away from 97 from 100, so root 95 or root 93, the farther we get away, this error is going to increase drastically, because what's going to happen? The farther we get away this way, the farther the curve is going to get away from the tangent, so the estimation is going to become worse. Makes sense. Okay, so let's look at a typical example you might find. This is the way I like to word them to make them clear. It says, determine the linear approximation L of x of f of x equals the cube root of x at a is equal to 8. Then use L of x to estimate the value of f of 8.05, which is, of course, the cube root of 8.05. So just to put this in context, this is essentially the root 97, and this is essentially a equals 100. So we know that a is equal to 8. If we plug it in, we're going to get the cube root of 8, which is 2. We know that. So we're going to make a tangent line out of that approximation in order to estimate the curve, which has the cube root of 8.05 on it, which we can't do on our head. That is the key. So what are we doing? We have our formula, L of x equals f of a plus f prime of a times x minus a. If we plug in our value of a, which is here, remember, you want to be careful with this, just because I've had students that plug in 8.05. That means you're probably not understanding, because the linear approximation is based on what we know. It's just like in the first problem, it was based on 100. We knew what the value at 100 was. So we based the tangent on that value because it's a known thing. Okay, if we find f of 8, we just plug 8 into our function, get the cube root of 8. F prime, well, we don't have f prime. We got to do that. So f prime of x. Remember, the cube root of x is x to the 1/3. So if we take the derivative with the power rule, 1/3 comes to the front. And then we have to subtract 1 from the original 1/3 and get 1/3 x to the negative 2/3. Everything must move to the denominator. It'll be 3x to the positive 2/3, which means we're going to get 1/3 cube root of x. And I'm going to write this a little bit differently with the square on the outside. FYI, it's legal to put it inside the radical or outside the radical. It doesn't matter which way we do it, okay? So just be clear that you can do it either way. I do it this way because it actually makes the math much easier the majority of the time when the exponent is outside. So then what do we do for f prime of 8? We plug 8 into that function, and hopefully you already see why the math is going to be easier, because the number inside here is not going to get crazy large, right? So all right, so we have our equation. Now we just got to simplify. So we got 2 plus cube root of 8 is 2, squared is 4, times 3 is 12. We distribute, get 2 plus 1/12 x minus 8/12, and we'll just write it out. So note 8/12 is going to be 2/3, right? Okay, if we put this all together and collect like terms, we're going to get 1/12 x plus 4/3 as our linear approximation. Okay, so what does that mean? That means right now on the curve cube root of x, I have gone to 8, and I have made a tangent line. That tangent line's equation is 1/12 x plus 4/3. Now, I need to use that line to make an approximation of f of 8.05. So what does that look like? That's going to be L of 8.05, which is going to be 1/12 8.05 plus 4/3. Now, just a note here, I don't want you to be confused just in case. So that wasn't in the denominator, that's here. Okay? So this is just a decimal value that you're going to get here, and a lot of them will be. So the approximate value I get is 2.004167. Okay, so This is the value on the tangent line that we're using to estimate the cube root of 8.05. Okay, so far the important things are our linear approximation and now our estimate the value part. So lastly, what we have to do is just see how accurate it is. That's not always asked for, by the way. Sometimes it's just find the estimate. But we're going to do it just to get practice. So percent error, okay, is going to be equal to 100 times absolute value of our our value that we approximate, our linear approximation, which is right above us right there, minus the cube root of 8.05 over the cube root of 8.05. If you want to put the decimal there, that's fine. I'm putting it here because I want you to see how close it is. So what does this value actually become? It's actually 2.004158. Look at that. So look at this value and look at this value. So again, just an incredible approximation we made by just taking a tangent line that's near the curve. This error actually ends up being 0.0004%, which is absolutely excellent. Like we can't, that's a really small error for our calculations. So we like this as a model for estimating, let's say, the cube root of numbers near very close to 8. Okay, let's try another example here. So this time we have the function 10 minus x squared, which we have at a equals 3. We need to determine the linear approximation for that. So if we went to that function, that parabola, upside down parabola, and we went to x is equal to 3, and we drew a tangent line, we need that equation, because then we're going to use it to estimate the approximate value of f of 2.8. So what, essentially plugging 2.8 in here. So again, what do? We go to our equation. So L of x is equal to f of a. So let's throw in our a's. So we'll skip this step, basically. We'll go right to the second one. So f of 3 plus f prime of 3 times x minus 3. All right, so what does that look like? Well, f of 3 would be plugging 3 in here. So let's write that out. I'll put it in square brackets so it's clearly defined. So that's going to be this, right? And then we're going to add, well, we need the derivative. F prime of x is equal to 0 minus 2x, which is negative 2x. So now I need to plug 3 in there. So negative 2 times 3, which is, so that is that. There you go, times x minus 3. All right, so if we do the math here, just out, this is 1, this is 6, and this is x minus 3. If we distribute and collect like terms, we're going to get negative 6x plus 19. So basically, this is our linear approximation that we start with. So this is important, obviously. All right, so where do we go next? Using this linear approximation, we need to estimate f of 2.8, which in our scope would be L of 2.8. So L of 2.8 is going to be negative 6 times 2.8 plus 19. If we do that, we're going to get 2.2 as our linear approximation. So that is our next important value, 2.2. Okay, so like I said, a lot of times they'll just ask for the linear approximation and then what the actual value of this is, we would be done. But if we want to find how accurate our approximation was, we can use percent error, which is going to be 100 times. We're going to do our linear approximation first, which is 2.2, and then we're going to subtract whatever 10 minus 2.8 squared is, all over 10 minus 2.8 squared. Okay? If we want to put that in brackets, that's fine. It doesn't really matter. Now note, this value actually ends up being approximately 2.16. So look at what we got. We got 2.2 right here. And then the value is 2.16. So we're actually getting farther away than what we're used to. And if we find that percentage, percent error is 1.85%, which means this is, I would say it's okay. It's like, I don't love that. That's a pretty good error. I don't love it, but I can deal with 1.85%. But, you know, we're not building bridges here, I guess is the best way to put it. Okay, so last problem of this section. Let's say we go to the rational function 1 over x, which we can estimate at 2. So clearly, if we plug 2 in, we're going to get 0.5. 1 over 2 is 0.5. So that's pretty easy. But why don't we try to estimate the value 2.5 and what that's going to be? It turns out that's actually really easy to do mentally too. But let's just, for argument's sake, go through the process like we've been doing it. So let's do L of x is equal to f of, remember, 2 plus f prime of 2 times x minus 2. If you plug 2 into here, we're clearly going to get 1/2, right? 1/2, I'll put brackets around it. But then we need the derivative. So we need to find the derivative of 1 over x. Well, remember 1 over x is the same as x to the negative 1. So the derivative of that is you bring the negative 1 to the front, you subtract 1 from the exponent and get negative 2. That means you're going to get negative 1 over x squared as your derivative. So what do we need to do? We need to take 2 and plug it in there. So we're going to get negative 1 over 2 squared, and then x minus 2. So this is going to give us 1/2. This is going to become minus 1/4 times x minus 2. And if you collect like terms and do all the fun algebra, you're going to end up with this as the equation of your tangent line, or your linear approximation. Okay? So what do? In the next step, we then estimate our value here by doing L of that value, 2.5. So it's going to be negative 1/4 of 2.5 plus 1. That is going to give us approximately, or actually exactly, negative 3.7 or 0.375. So that's our approximation of 2.5. Okay, so again, we need to find the percent error. So percent error is going to be equal to 100 times our linear approximation, which is 0.375, minus 1 over 2.5, which, by the way, is going to be 0.4, which I'll write down here. Okay, that's going to be 0.4. So now we're at 0.4 and 0.375. So it's really getting far away here. Let's see what that calculates to be. 13.75%. That is an ugly percent error. Not good. Okay, so that would tell us that we would not want to use this model of linear approximation to estimate so far away from 2. So you might be like, 2.5 is not far away from 2. And it actually is in terms of this process. You want really minuscule values like 0.1, 0.01. That's what you're looking for. But this is the process for doing linear approximation.